So the big idea here with the warm-up is let's think of what we know already. We know how to find the area between curves, right? And that was the integral of the function's top minus bottom, or however it was set up. Well, now if we have volume, volume is the accumulation of the area all added together. But we have to think of this very creatively. So find the volume of the solid generated by revolving the region around, in this case, we're going to go around the x-axis. So what's going to happen is this green area is going to rotate off the page and physically come up, and then rotate here, and then go behind the smartboard. So it's going to rotate around and come back. So picture a three-dimensional image. Well, what I like to do is picture this point. Now we know this point is 2 units up. Can't see it, that's a 2. So I have to go down 2 units. I'm going to put a dot. And technically, any other point, if you wanted to pick a bunch of random points, all of these points are going to be reflected down, which is just going to make this line reflect over. So now, what's going to happen is we need to visualize that or draw that three-dimensionally, which is kind of hard to do. So I pick a point up here, and if I rotate it, it's going to come off the page, and then it's going to hit this point, and then it's going to go behind it. So kind of picture that as like a cone, and that's exactly what this image is. It's a cone that is just tip on its side. So I always like to draw a couple. I don't go crazy, because otherwise my picture's going to get really messy. But pick another random point, and let's rotate that. And then if I pick another smaller one, what's happening? The volume is the accumulation of all those circles, or we're going to call them discs. It's the accumulation of all the discs added together. So what we need to do is we need to just pick one of those discs, and we call that a cross-section. And that cross-section is just a circle. And we know that that circle has a radius, right? And since if I picture an infinite amount of these discs stacked together from left to right to make up this cone shape. So if I add up the area of all those infinite amount of circles, that will give me the volume. So what do I need then? I need to find the area of this circle. Well, area for any circle is pi r squared. And that's going to be true anytime you have a disk. You'll always use pi r squared. But the big question, and one of the harder things to do, is what's the radius of this circle? Well, the radius is tied into the given equation. Because the radius is from the x-axis straight up to this function, which is whatever y is equal to. Right? That blue length right here, this radius, is the output. Okay? It's however large the output is. So what does that mean? I need to take this equation, and I need to solve for y. So we've got to do a little bit of algebra. You can do that in your head if you want to. I'm going to do part of it in my head. I'm going to bring the x over. Doesn't matter how it's written. And then I'm going to divide by 2. And there's my equation that will give me the length of the radius. So what is the radius? Let me rewrite this a little bit here. My radius is negative 1/2 x plus 2. So what would the area formula be? It would be pi times the radius squared. Now, you can get as crazy as you want algebraically to simplify that, but to be honest, I'd leave it right now. So what is volume? Well, volume is the accumulation of whatever you said your area was. This whole thing is my area. I'm just going to replace it. I'm going to do one thing here. Notice I forgot a pi. I did that on purpose because pi is a constant, right? If pi is a constant, we know in integrals I can float the pi on the outside. The only thing that's left over are my bounds. So how do I know what the bounds are? Well, let's look at how are the circles stacked up. Where's your largest circle? The largest circle is at x equals 0. And then they stack up from left to right, so where's the smallest circle at? I know that's hard to see, but that's at x equals 4. So we're going to go from 0 to 4 as my bound. So we're going to pause right there. That's the new material. Okay? All of this, getting it set up, that's the new material. Everything else after this point is just, can you evaluate the integral? And we've done that many, many times, so I hope you kind of pause here and say, okay, I'm comfortable with, maybe I still have questions, but once I get to this point, I'm comfortable solving. So let's do this because I don't want to waste a lot of time. Let's plug this into our calculator. I'm going to give you a hint. Leave pi out of it. Okay, just plug in the integral part, and let's see what our answer is. Make sure you're really careful with your parentheses as well. And then turn that answer back into a fraction over there. You get 16 pi over 3. Okay. Now you should be able to get the same thing whether or not you do that by hand or on the calculator. So I know you still have questions. And I know you're probably wondering, how do I know what the bounds are? How do I know if it's dy or dx? And how do I know what the radius is? Is it written in terms of y or an x through x? And my hopes are to answer all of that once we get done with this example. Okay. Hello, welcome. Good to see you again. Yeah, wherever you want. This is Miss Hess, former Titan grad. So we're going to take this exact same area, but this time we're going to revolve it around the y-axis. So we want to visualize that three-dimensionally coming off the page, rotating kind of as we go up and then to the left. So let's mimic this. We know that we're going to go all the way from 0 to 4. So if I rotate this point over to the spot where it says -4, that line is just going to be present here. And that gives me kind of that reflected area over the y-axis. Now, as we did before, we're going to draw those same circles. But this time, our solid is a cone that stacks up from the bottom to the top. So, this is where my skills at drawing, let's see how good they are. not perfect, but there's the first lower circle. And then pick another random point, anywhere in the middle. Reflect that over. Draw another circle. Again, you don't really even need the pictures if you can visualize all this in your head. And then if I do a really tiny one up top, hopefully the idea is you see that visualization of the solids on the bottom stacking up from the bottom to the top. And what is my cross section now? It could be any one of these circles. I'm just going to pick this random one that's kind of poorly drawn. You really don't need the picture, but I'm a visual learner, and that's always really helped me understand where things come from. So it's still a circle, it still has a radius, and we are still going to use the same pi r squared area. But now the challenge is what is that radius? So the radius now starts from the y-axis and it goes all the way out until I hit this spot. So notice, this length is a length from 0 to some random spot, but it's in terms of x. So I need to write this equation as x equals, which is a lot friendlier than the other one, right? So I'm going to solve this for x just by moving the 2y over with subtraction. And again, I know that you're probably not super comfortable with that. I'm going to give you a big hint once we're all done. So there's my radius. And then I'm just going to plug that in as well. Negative 2y plus 4. Now we have everything we need to set up the integral. And again, the integral is the area of each disk added all the way up. So volume is going to be the area of the circle, so pi times radius squared with respect to y. So now the questions are, what are the bounds? What bounds go here and here? Well, where's the lowest circle lie? It lies right here at y equals 0. So we're going to start at y equals 0, and then those circles stacked on top of each other, when do they stop? At y equals 2. And there it is. That's the new part. I'm hoping that even if I gave you this, you could do this by hand. You'd have to do some algebra and FOIL it out. But we want to save time, and let's just grab our calculator and see what that looks like. You get 32 pi over 3. Okay. All right, so let's look at some patterns here and try to make this a little friendlier and answer those questions that you might have. How do you know what goes where? I'm not sure if this is going to get pretty crazy with my highlighting, so don't follow me highlighting here. But let's look at this. What if I tell you to revolve about the x-axis? Look at how your circles are stacked. They start at x equals 0, and they end at x equals 4. So we're stacking from left to right, which those are my bounds. Now, here's another hint. X-axis, dx. That's a big hint. X-axis, x is in the radius. So everything has to be written in terms of x, including the bounds, the radius, and dx. Now let's go to the y-axis. If I rotate about the y-axis, my equation has to have y in it for the radius. So we're solving the expression so y is in the problem. The big circle starts on the bottom at y equals 0, and it's stacked vertically at y equals 2. So everything should, if you're revolving on the y-axis, everything should be written in terms of y. The bounds, the radius, and dy. Same thing with dx. Now I know you're still not super comfortable, and that's fine. We'll get there. I don't want to write this. I actually want to go pretty quick, but maybe just think about this. What if I asked you to find the area of that washer, right? The bluish area. How would you do it? Physically, what are you thinking of doing? Perfect. Area of the big circle minus area of the small. So we're not going to write this today, but if I took the area of the big circle minus area of the small, well, let's think of that really more in terms of formula. Big circle's radius is 9, small circle's radius is 5. Before I get too creative, they both have a pi in common, right? So why not shorten it and just say the radius of the big one squared minus the radius of the small one squared times pi will give me my answer. Right? So 81 minus 25, whatever that is, that's your answer. Now, in general, and this is really getting at what we're doing today, how would we write that if we didn't have numbers? Because we know we're not going to. They're going to be some type of equation for the most part. Well, what is it? All it is the large radius squared minus the small radius squared. And that will represent this area. So are we comfortable with that? Because that's our big skill today is what happens now when I don't have a specific disk? It's not a complete circle. What if it looks like a washer? We still know the area formula for the washers. So, officially, we're titling our notes, 8.2 day 2. We're looking at finding volumes of solids of revolutions again. So the directions are still the same. We're still going to rotate about an x or a y axis. The only difference is instead of getting a filled-in disk, we're going to get a washer. Okay? Now, I don't want you to write this because this is just visualization of where we've been to where we're going. So just kind of watch this one quick. I'm going to do it probably pretty messy, but pretty quick. If the solid is rotated about the x-axis, what is the shape of the cross-section? So here's the x-axis. If I rotate this point is up maybe close to the 6-ish. It's going to rotate down. And then there's my spot. And then if I rotate these points, you can see the cross-section shape is a disk, right? And the area formula for that disk is just pi r squared, and all we need to know is the radius. And the radius will be written here in terms of x, which is right there. So, that's what we just finished with. But what if my graph now looks like this? I'm still going to rotate about the x-axis. There's just more to rotate. You have to be very careful with this. Now, this is the red graph is the exact same thing we did up above. So I know it's going to look something like this, and this point will rotate down to here. And then the blue portion is also going to rotate about the x-axis. This point will stay. This point looks to be just about 3. So I'd rotate that down. And that, you could shade that if you want. But now when I rotate, this point right here is going to create a circle. But then the blue point is going to create a circle again. And you see your cross section. Now if I pick a random point up here, okay, what if I do this? I'm going to make it a little closer. If I'm in here and I just go straight down, there's a point here, here, and here. This one would reflect, and it would be dotted back here. Reflect a little bit of a circle there. And if I did this point, notice the blue is not really part of it. And reflect down, and this part is just a disk, but everything works its way out. And really, the overall cross-section is this wash. How do we want to think of that? Well, we want to think of it as there's a big radius that goes all the way up to the highest function, which we already know. And then there's a small radius, which starts at the same point, but it only goes to the blue function, which we already know as well. So, what would our area formula look like? It would be pi r, oops, very careful here. It would be pi r squared. However, we saw in the last example, it's a lot friendlier to write it as pi capital R squared minus lowercase r squared. If you don't like that, you could redistribute the pi and just say it's the big circle minus the small circle. I have kids that just, they didn't love this, but they knew the area of each circle. Okay, so we could plug those items in, and then what is volume? Volume is always the area of whatever shape we have, the integral of the area. So the only new part today is this part right here, the washer setting up that equation. And if you take that away from it, you're hopefully going to see the connections of this stuff isn't that bad. Don't think there's any volume to this, but I don't always trust my drawings, so I want to give you guys just a quick, much better visual. So what if I have two curves? You can see the top curve is a square root function, the bottom one is linear, and we stop at x equals 4. Here's my shaded region. What if this region is rotated about the x-axis? So that's the shape that we tried to draw. And hopefully you're able to visualize that. But what if I cut a small section out of it, the cross section? What does it look like? It's the washer. So that's just a visualization to help you guys see. Now technically the thickness of this is why, that's the change in the x's. We call that dx. So I might hint at that. But there's a reason why dy and dx are in the integral. And it results or it relates to the width of an item. All right, let's try this one. Now, notice the directions right away. Use your calculator to evaluate. So we're going to set this up, and then we'll use our calculator to save time. Try to make that bigger. I think I can do this. There we go. Now sometimes they'll give you a graph. Sometimes, like we saw in the homework the other day, you have to create the graph based off of your knowledge of what you know from all the functions that we studied, pre-calc, calculus, and before that. So we've got the equation y equals 2 times the sine of x. Well, we know sine starts at 0, 0. And we know it usually goes up to 1 for a maximum, but that 2 doubles it. So that's why we're going up to the spot of 2. And then we're stopping at y equals 0. And y equals 0 is just the x-axis. And then they tell us we want a vertical divide at pi over 2. And pi over 2 is a maximum of some. The directions tell us to revolve this solid around the y-axis. So visually picture that going over to the other side. We're going to redraw it the exact same distance away. We know that this would be at negative pi over 2. And then we're going to go up to positive 2. Now here again is a hint. We're revolving around the y-axis. So your washers are going to start at the lowest y-value. They're going to start at 0. And then this one actually is a disk because it touches right at the same spot, but you don't have to worry too much about that one. And what if I rotate the top one? That's really just a circle. It's the bottom or the middle piece that creates that washer. And that's why I like to highlight. These drawings can get pretty involved. So now the question, and usually it's the hardest part, is what are the radii? We know we're going to have a large radius, that's capital R, and then we know we're going to have the small one, which is lowercase r. I usually just write those down below. Let's picture what that large radius is. It's going to start at the y-axis and it's going to go all the way out until you hit this line. Well, how long is it along the x-axis from here to here? Pi over 2. And there it is. It's not an equation. I mean, it kind of is. It's a constant. That's just the length from the y-axis out to this line. And notice, that's true in every circle we look at. Down here, or even up here, all of the big radii are pi over 2. All right, now, what about the small radius? That starts at the same spot, and it goes until it hits the blue curve. Well, here's our hint. We're revolving about the y-axis. My radius has to have y into the problem, into the equation. So I know the blue curve is y equals 2 sine of x. Well, that's not written in terms of y. We have to do algebra, and we have to get rid of, we have to move everything over so x is by itself. So do however much you need to in your head, but I'm going to divide by 2. And then I have to get rid of the sign I'm going to call that sine inverse. And there's the length of this blue radii. Now notice, that's true at any point, even right here when it looks like it doesn't exist. And the reason why is if y is 0, the inverse of 0, sine inverse of 0 is 0. So there's reasons why that's true. And then same thing here. If you plugged in 2 times 1/2 is 1, sine inverse of 1 ends up giving you that same value. But I think that's the hardest part about today. Determining what the radii are. Now, the more you do this, you don't have to write the area formula out separately. You can do it right in your integral. I just like to provide you with a little more detail. The area of that washer is pi times the big radius squared minus the small radius squared. And we already know what those are, so you can plug those in. Do be careful with parentheses, because you're squaring the entire radius. I need more room. And then we can write our volume, which is just that area expression put into the integral. I'll ask you guys. What goes at the end of the integral? dy. How come it's y? We're rotating about the y-axis. I have y in my equation, so I have an end in dy, and that means my bounds. That's another thing that kids make errors on. What are the bounds here? They have to be in terms of y, so what's the lowest y value I hit? 0. What's the highest y value I hit? And then this one, we would do in our calculator anyways. So go ahead and give that a shot. Again, leave pi out of your answer until the end. And you should make sure you're in radian mode as well, because we're doing trig functions here. If you're not in radians, it'll screw everything up. It might take your calculator a while. I know the TI-83s, mine has been going for about 30 seconds trying to calculate it. So don't think your calculator is broken. Don't think it's stuck. It takes some time. And then eventually you'll get there. And I got 4.000000. We can round that to 4. So 4 pi. How are we feeling right now? Give me a quick thumbs up, thumbs down, based off of maybe how you walked into class today versus how you feel right now. Hopefully we're trending upward. And that's the idea, is this stuff isn't super easy. Once you get the hang of it, it's very routine. All right, let's Let's not do this one. Let me see. Okay. Yeah, we're gonna save this one for tomorrow. What I'd like you guys to do is we got 23 minutes. We're going to take this scenario and we're going to try to revolve it around the x, the y equals 2, and you might not be ready for part C and D. And actually in that case, let's not do D, let's just do C and see how you do with that. I have the answers here. So as you go, you can check them, and for time's sake, let's do all this in our calculator. It says setup but not solve. What I mean is just plug it in your calculator to get your answer. Okay? And now is a perfect time. If you had a question on maybe one or two items, we can go through this. And we'll give you about 10 minutes of work on this. All right, so here's part B. If I rotate about the y-axis, then this point right here, which is 4 units away, is going to rotate over about 4 units on the other side. It'll look like that. And then when I create my rotations, that's going to create a big circle up top. If I pick a random point at the bottom, or maybe midway through, that'll create another point. And you can see that they are just discs. There is not a washer here because there's not a hole. So one of the challenges is just being able to change your thinking. And in this case, you only need one radius. Okay? What is the radius of that cross-section? Well, if I start at the origin and I go out until I hit that curve, this curve was y equals square root of x. But we are revolving around the y-axis, which means I need y to be in the equation. So you have to do a quick solve. If you square both sides, you end up with y squared equals x. And there's your radius. And I know that area is pi r squared. So if the radius is y squared, I'm going to square the squared. And the volume would be, I'll just do this. You could write it as y to the 4th if you want. And then what are the bounds? The bounds have to be in terms of y. What's the lowest y value I get? 0. What's the highest y value we get? 2. And then when you calculate that, your answer should be 32 pi over 5. If you can confidently say that you're good with part A and B, you're in a really good spot right now. I decided to throw part C out there just to see if you can do it. And let's look at that one really quick here. So here's part C. They're telling us now to rotate about the line y equals 2. Okay, so that, picture this, it would be kind of like if we rotated about the x-axis. So we are still rotating with respect to x. So everything has to be written in terms of x. dx, your equation. But when I rotate this point that is 2 units away, is going to come up here. It'll look like that. And then when I pick my points, I'll get a circle out here. I'll get a circle in here. Maybe another circle here. But that's my cross section. So I just need a radius. The radius is tricky though. Well, I like to draw the radius in right here. So we have to be careful. Okay? What if I drew it all the way down to the x-axis? How long is that blue line? 2, right? The blue line is 2. How long is it to this little mustardy yellow line? and the x-axis to the curve, this yellow line is y equals the square root of x. We don't want the yellow line, we don't want the blue line, I want the difference of the two. I want a green line. So the radius is the large 2 minus the square root of x. And like I said, I didn't expect you guys to be there today. But on Monday, that's what we're going to start looking at, is little things when we don't rotate about an x or a y. And then, there we go. So, homework tonight is on Schoology. It's a couple problems. The answers are posted on there already, so use those answers to check as you go. Anybody on Zoom, if you have questions, you can stop into our after school hours from 12:55 to 1:30. Have a good day.